Hello everyone, Chapter 3, Lesson Delta, Graphs of Sine and Cosine Functions. Objectives are to look at the graphs of sine and cosine, as well as the attributes of each, to talk through the transformations performed on sine and cosine graphs, as well as write a sine or cosine function given a graph. So without further ado, let's get it going. Okay, so we're going to sketch graphs for a sine and cosine function. So I have defined independent variable x and the output of sine x. So for example, y equals sine x, its table of values would look like the following. I've picked these inputs because they are all very nice function inputs that give us very good numbers, okay, along the way. So let's go ahead and we're going to plot each of the x's and their appropriate y's, where x is the independent variable and sine x, or y, is our dependent variable. Now if you look at the table of values, the max possible outcome that we see for sine x is an outcome of 1. And we see that once here. So what we're going to end up doing is going through one cycle, or one period. We're going to graph one period of the sine function, and then we'll see how that period repeats itself. So a period is one cycle. Let's go ahead and plot some points. Here's the point 0, 0. That's the x and y axis, or x and y intercept, first x and y intercept for both, for the sine function. Okay, and then I'm actually going to go ahead and go out to pi over 2. So I'm going to go out to this value, and I'm going to fill in some values in between. So this is x equals pi over 2. The output is 1. Then I'm going to go over to pi at pi units, which is 2 pi over 2's. So the distance between 0 and pi over 2 and pi over 2 and pi is equivalent. We're going to see some symmetry here. Then I'm going to go to 3 pi over 2. 3 pi over 2, which its output is negative 1. We're going to look at how this equates to the unit circle to the right here in just a second. And then we're going to go out here to 2 pi, which comes back to 0. So let's look at our values in the table and see how they match up here. So of course the sine function is the y value, right? When we look at the unit circle, the y value. So our y value when theta is 0 is 0. Our y value when theta is 90 is 1. Our y value when theta equals pi, or 180, is 0. Our y value when theta is 3 pi over 2 is negative 1, and then we come back to 0. Now the others fill in appropriately along the way. They fill in a way, let's go 1/2, there's pi over 6, 1/2. There's, oh goodness, is my pencil not working here? Let's see. Oh, it's dead. All right, I'll be back. Okay, let's see if it's working now. And yes, it looks to be working. So root 2 over 2 for pi over 4. And then root 3 over 2 for pi over 3. So our function value, our sine function, is going to curve, make this nice, smooth, symmetrical shape from 0 to pi. And it's going to come down, hitting a minimum of negative 1 when the input is 3 pi over 2, and it completes one cycle. And the reason why I say it completes one cycle is because then the pattern will repeat itself. Pause the video and tell me whether or not you can determine that value right there. Well, that value right there is going to be 3 pi. All right, now look at, here is one cycle of sine function. And one cycle, or one period, is equal to 2 pi radians. So if I went from pi out to this point, that's another cycle of the sine function, just in a different orientation. That length should also be 2 pi. Okay, let's go ahead and move on to the cosine function. A couple of last things to note. Okay, maximum value of the sine function is attained, provided there's no transformations, is attained, its first max value would be at pi over 2, comma 1. Its first minimum value would be at 3 pi over 2 and negative 1. Okay, and then we repeat max values every 2 pi units. So this one would be the next max value, and then and on, right? So pattern recognition in this. Let's look at cosine. So cosine is the x value within the unit circle. So notice how the y value here started at 0. Where do you suppose the x values start in the unit circle? Well, they start at 1. So our first point on the cosine function, at least starting at 0, will be the point 0, comma 1. All right. Then I'm going to go out to pi over 2. And at pi over 2, we get an output of 0. Then I'm going to go out to pi in a similar way that I did with sine. And at pi, our output is negative 1. And then I'm going to go out to 3 pi over 2. And at 3 pi over 2, our output is 0. And then I'm going to go out to 2 pi. And at 2 pi, our output is 1 again. Filling in the appropriate values along the way. I'm going to kind of skip over that for now, just for time's sake. But the graph of cosine will look something like that. I don't like exactly how I did this between. I don't like that either. Let's do it one more time and see if we can get it. Yeah, it's better, but it's not perfect. Okay, so that's the first cycle of cosine. And cosine has one period equivalent to 2 pi radians as well, right? It cycles back through, and it'll continue in the same manner, actually in both directions. Okay? All right, so there is the beginnings of sine and cosine. Of course, our first max value is attained at 0. Our first min value is attained at pi. Our next max value is attained at 2 pi. And that'll be attained at the output of 1. Okay, so in this lesson, this is just baseline knowledge on how to graph sine and cosine. I like to think of, when I just see these graphs and I don't have a label of which one's which, you can tell that the first period of cosine kind of looks like an upside down C, and the first period of sine, right, kind of takes on the shape of a sideways S. Right? So that's one way that you can visualize which one's which. Of course, sines and cosines, I mean, they are very closely related, so we have to be careful depending on how the function is oriented. But in general, with no transformations applied, you can use those two visual rules with the upside down C, or the sideways C, and the sideways S. Okay, so let's continue on with some transformations. Okay, so the various transformations that can be performed on sine and cosine come in the following form. Okay, I want to isolate or identify A and B and C and D. Okay, so there's nothing different between these two equations other than the fact that one has a sine and one has a cosine. But both of the equations, the values for A, B, C, and D do the exact same transformations. Everything is the same, it's just the original parent function. So we're going to perform parent function transformations on sine as well as on cosine. Now, what do each of these values do? Well, A represents a number of things, one of which is the vertical stretch or shrink. Okay, now the vertical stretch takes place if A is greater than 1 or A is less than negative 1. Okay, and I'll talk about if A is negative, how that affects things too. So that's a stretch. If A is greater than 1 or less than negative 1. A shrink is attained if a is between -1 and 1. All right, that's when a shrink will happen. So for example, if I had y equals 1/2 cosine of x, that would be a vertical shrink by a factor of 1/2. Okay, now a third thing that comes up is if a is less than 0. So it could be a shrink or it could be a stretch. But if a is less than 0, then we have a vertical reflection. So 3 things to be aware of: the vertical stretch and its values of a, the vertical shrink, its values of a, and then the vertical reflection and its values for a. Okay, B. Let's talk about B. First thing that we want to note is that you can see that B is factored out if there's also a C value. So for example, if I had y equals sine of 2x plus 4, the first thing you always want to do is you want to factor out that B value. Okay, when I factor that out, that gives me the true value of C. That is C. This is not C. 4 is not C. Okay, C is located and identified once B is factored out. So we want to factor B out immediately. Now, what does B do? Well, the period is determined by using B. The period of any sine or cosine function is equal to 2 pi divided by B. All right, so if, let's take this example, y equals sine of 2x plus 2. All right, here B is 2. Therefore, the period which used to be 2 pi is now 2 pi divided by 2, which means the period is pi, which means that the graph has been shrunk by a factor of 1/2 horizontally. Now, just like with other parent functions and their transformations, that number on the inside is deceptive, right? You think a 2, you think a stretch, but on the inside, it's always the opposite, right? So this would be a horizontal shrink. So let's talk about that. So this would be a horizontal stretch given that B is less than 1. Okay, actually I want to restate that. Given that B is between 1 and -1. All right, similar to the shrink vertically. It'll be a horizontal shrink. I can spell things. If B is less than -1 or B is greater than +1. Okay, there will be a horizontal reflection if B is less than 0. Okay, so again, 3 things here. We've got horizontal stretch when B is between those 2 values. We've got a horizontal shrink when B takes on one of those 2 values. And we've got a horizontal reflection if B is less than 0. Okay, so what is C? C is called the phase shift. And the phase shift is the horizontal shift. You can think of it as a slide to the left or to the right. Okay, so you want to be careful with this. If you have an x plus 2, then you're going to shift to the right. If you have to the left. If you have an x minus 2, that's going to be a shift to the right. So for example, in our y equals sine 2x plus 2, that's going to be a shift left 2 units. Okay, so that comes with a little bit of experience. We'll get a few opportunities on the slide coming. Okay, and finally, D is very simple. It is a vertical shift. Okay, if D is greater than 0, it's going up. And if D is less than 0, it's going down. moving that function either up or down. Awesome. One quick thing that I do want to talk about is called the amplitude. Okay, and the amplitude is very closely related to A. The amplitude is the vertical stretch, but the amplitude is special because we only consider the amplitude a positive value. So to find the amplitude, you just take the absolute value of A. So if the function has been reflected vertically and A is -2, we only call the amplitude +2. All right, let's get into some examples. Okay, so let's first talk vertical stretch, shrink, and vertical shift. Okay, so I'm going to take the parent function. Let's call the parent function here y equals sine x. And I'm going to plot a few points. Okay, and I'm going to talk through some stuff here. So I'm going to go 1 and -1. And I'm going to go pi, 2 pi. And I'll go in between with pi over 2 and 3 pi over 2. All right, so our sine function, generally speaking, would look like this. Here's our parent function for the first period. Now what I'm going to do to this function is I'm going to shift it up 2 units and stretch it by a factor of 3. But I prefer, personally, I'm going to stretch it by a factor of 3 and then shift it up 2 units. So just thinking of this, here's what I call the center line of the function. I'm going to send this center line up 3 units. Excuse me, not up 3 units. I'm going to send it up 2 units in just a moment. But first I'm going to stretch the function by a factor of 3. So that's going to take this value right here, and it's going to stretch it from 1 up to 3. Okay, and then it's going to take this point right here, and it's going to stretch it from -1 down to -3. So let me sketch that real quick. And just to save a little bit of heartache, I'm going to save myself some space. Here is approximately what this graph would look like if I just did a vertical stretch by a factor of 3. I always do the vertical stretch and then the vertical shift. Okay, now I'm going to take my baseline and I'm going to move it up to 2. 2 units up, right? So here's the line y equals 2. That means I've got to take this point, which was at 3, and also shift that up 2 units. I'm going to move that up. I'm going to put this in yellow, up to 5. Okay, so it's going to move that point up to 5. It'll move this point up to 2. It'll move this point up to 2. It will move this point, which was at -3, and it's going to move it up 2 units to -1. And it's going to move this point and move it up to that new baseline. So our final transformation, this is not perfect by any means. I might have underestimated my my sketch on the top portion got scrunched a little bit. But I have stretched it by a factor of 3 and then shifted it up 2 units. So this is the graph of 3 sine of x plus 2. I would label all these points too. I would say that this is pi over 2, comma 5. I would say that this point is the point 0, 2. This point is the point pi 2, 2 pi, 2, and this point down here would be the point 3 pi over 2, -1. Okay, perfect. Let's do a cosine function here. Take a look at what's happening there. Okay, let's graph the original cosine function. Looks like there's a vertical reflection here. So cosine function would have the following. This would be pi over 2 and pi and 3 pi over 2 and 2 pi. You're going to get used to just putting these. Oops, I don't want that. I want this. these three I call them staple points, just kind of gets you where you want to be for maxes and mins, and then in between. Okay. All right, so there's cosine. Now I'm going to do a vertical reflection first. So I'm going to reflect vertically, taking that point down to here. This point will stay in the same spot. This point will come up and become a max. That point will stay in the same spot. And then we reflect that one as well. So we get a vertical reflection. So this function would be negative cosine of x. And now to get the second vertical transformation on that, I'm going to shift everything down 1 unit. That's going to take every point down 1 unit. This one will come down to here, to there, to there, and to there. So I should get a graph that looks like that. Now, I haven't changed the period at all on any of these functions. You can see that the cycle is still 2 pi units. Nothing changed there. Same thing up here. Cycle didn't change, so the period has not changed. We've only been working vertical transformations. Okay, so let's take a look at some horizontal transformations, and then we'll get into some graph identification. Okay, here on this next example, we're going to talk vertical and horizontal shifts. Oops, I wanted this to be horizontal. My bad. Notes off. I want this to be horizontal stretch shrink. I'm a Bears fan, so I like blue and orange, which will be represented by B, and the horizontal shift, which will be represented by C. Now, I wanted to take it kind of slow going into this because I want to identify and be able to work with how this is a horizontal, well, in this case, you could tell yourself, but this is going to be a horizontal shrink. Okay, so we said that the period is determined by taking 2 pi, the normal period, and dividing by B. Okay, so I'm going to get a period of 2 pi over 3, which means I'm shrinking this function by a factor of 1/3. Okay, so let's graph sine again, and I'm going to graph sine the full period out a little ways. Okay, and sine looks like an S, as we mentioned earlier. This would be pi over 2. This would be 3 pi over 2. And of course, this would be 1. Oops, I'm sorry, that's for our cosine function. This would be 1. So our graph will take on this image, this shape right here. Okay, not perfect and definitely not to scale, but that's okay. I just want to get the generals down. Okay, so what this is going to do is this is going to take our graph, and every one of these special points is going to be reduced by a factor of 1/3. So it's going to take 2 pi over 3, or excuse me, 2 pi, and shrink it down to 1/3 of its size. Okay, let's say this is, it's probably pretty close. Let's go here with it. This is 2 pi over 3. Okay, so I took this and I divided it by 3. Now, what would happen if I took this and divided by 3? Well, the 3's would reduce and I'd get pi over 2. So that point is going to shrink down to, oh yeah, my first point was off a ways. I'll adjust that in a second. Okay, what if I took pi and I divided by 3? Well, I'd get pi over 3. Okay, and then what if I took pi over 2 and divided by 3? Well, I'd get pi over 6. So my point here, let me scratch this out. This point was off slightly. I wasn't estimating very well. But you can see as I now sketch the graph of my sine function, the period there from 0 to 2 pi over 3, which is a period of 2 pi over 3 radians, is 1/3, right? 1/3 of the original period. You can see there's 3 2 pi over 3s that make up 2 pi. Okay, that is definitely, I think, one of the easiest ways to do horizontal shrinks and horizontal stretches. So let's go the other way with it. Let's work with a cosine function. And then we're going to get into one that's a little bit more complex down below, okay? So cosine, of course, and I'm going to start to become a little bit more free and easy. Oh, I don't want to do them that far apart. Let me do this. I'm anticipating the example I put up here, which was that I'm going to double the period. Okay. And I'm going to do a reflection, it looks like. So this would be pi, this would be 2 pi. And I'm assuming that I know that that'll be midway in between, so it'd be 3 pi over 2, but I'm going to save some space. Same thing over here, this would be pi over 2. Okay, so what I'm going to do is I'm going to do the horizontal stretch first. So I'm going to take 2 pi over 1/2, which is now going to change the period from 2 pi. So period will equal 2 pi over 1/2, which makes the period equal 4 pi. So we're going to stretch this thing out. It might be okay, proportionally speaking. Now it's going to take this point, which was pi over 2, and it's going to double it. It's going to bring it over here. Okay, and it's going to take this point, which was at pi, and double it, which is going to bring it over here. Okay, and it's going to take this point, which was at 3 pi over 2, and double that, which will put it at 3 pi. And it's going to take this point here, which was at 2 pi, and it's going to double it. Put it right there. Okay, so let's connect this thing. It's going to sketch the graph. I probably should do a different color, but I'll just go, I don't know what to go right now. Haha, I found it. I'm going to stretch it out, stretching this function out, going to all my new translated points. That is the graph of y equals cosine of x over 2. Now, I do have to do a vertical reflection. Nothing will change with the locations of each of the points. What I'm going to do is just take each point and reflect vertically. So now I'll go down to -1. At least any point on the horizontal axis, the x-axis, theta axis, whatever you want to call it, won't change. But now I get my final product, which would be negative cosine of x over 2. There's a vertical reflection. And I might ask you to give me some points. Of course, this is 4 pi -1, and this is the point 0, -1. This is the point pi 0. This is the point 2 pi, comma 1. So just get used to labeling these points at the very end. And you can confirm that those points work. You can plug them in to the original function and see if everything lines up how you want it to. Okay, let's get to this last example on this slide. Okay, so what was the first thing that I told you to do with regards to b, right? I told you factor. So factor out that b value. If I take a 2 out of 4 pi, I get 2 pi. So what's going on here is that we've got a change in the period. The period is now going to be 2 pi divided by 2, which means the period will be pi. So I'm shrinking it horizontally. And I'm also doing what? What does the -2 pi do here? That's a shift. It's a phase shift. Right 2 pi units. Okay, so I'm going to do the operations in the opposite order that you'd expect. So I'm going to work from the outside in. So I'm going to do the shrink first, and then I'm going to do the phase shift. So first things first, let's plot the parent function. Let's plot sine. Okay, it looks like an S. +1, -1. I got 0, 0. I got pi over 2, 1, pi 0, 3 pi over 2, -1. My writing has gotten worse. And 2 pi 0. Okay, so the function looks kind of like this, blah, blah, blah. We're getting used to this. Sideways S, perfect. Okay, so I'm going to do the period change first. That means I'm going to shrink the function by a factor of 1/2. Okay, so instead of cycling every 2 pi units, we're going to cycle every pi units, just like that. Okay, I'll label this point. This will be the point, what is that, 3 pi over 4, comma, -1. This would be the point pi over 4, comma, +1. And then, of course, we know these would be zeros at each of those values. Okay, now I'm going to take this function and I'm going to shift it 2 pi to the right. So that means I'm going to take all points and shift them. But in order to do that, I got to go out here to 3 pi, right? Because I see if I'm going to shift this point at pi, 2 pi units to the right, and I'm going to shift this point here at 0, 2 pi units to the right, this red function is going to start here at 2 pi and end here at 3 pi. Granted, the function never ends, right? It never stops. So it really doesn't, but check out what I'm going to do here. I'm going to sketch the next period, and I'm going to sketch the third period. So if I were to shift this gray portion of the function right here, it would line up perfectly, or should, with the red portion, or the blue portion here. Okay, which would make this point here, oh gosh, hold on, let me do this. 4 pi over 2, this would be 5 pi over 2. This would be 6 pi over 2, so 3 pi, comma 0, 5 pi over 2, comma 0. This would be 2 pi, comma 0. Yeah, so that's where our function would land. I'm blanking on what these values would be here, but let me think about it while I write this out. So this would be 9 pi over 4. So this is 8 pi over 4, 9 pi over 4, 10 pi over 4. This would have to be 11 pi over 4. Okay, so there you go, guys. Remember, factor out b, then you get your true horizontal or phase shift. All right, let's move on to the next slide. All right, guys, I'd like to do a multiple transformation sketch here. So let's take cosine, and let's do a horizontal shrink, and then a vertical stretch and a vertical shift. So a horizontal shrink would take our original period, which was 2 pi divided by 3. So I'm going to draw our new function, or at least our new period length. This will be 2 pi over 3. This will be pi over 3. This will be pi over 6. This will be pi over 2. Okay, fractions, love them. Okay, I'm going to stretch our function by a factor of 2, but then I'm going to shift it down 4 units. So what would have been here at a +2 is now going to be down here at a -2. And what would have been at -2 is now going to be down at -6. Okay, so I've shifted both the upper portion and the lower portion of the function, their max value and min value, is down 4 units. All right, so the midline would be right here at -4. Now I can just sketch my function to look just like a cosine function, and attaining those max and min values right like that. So this would be the point pi over 3, -6. This would be the point pi over 2, -4. This is the point 2 pi over 3, -2. This is the point pi over 6, -4. And this is, of course, the point 0, -2. And there you go. There you have one period of cosine of 3x minus 2. All right, let's look at the second one. Looks like we're going to have a change in the period length. We're going to have a shift. Looks like to the right pi units. We're going to have a vertical reflection and a shift up 1 unit. So let's identify the baseline here in a second. Looks like our baseline will be determined by this +1. So we're going to have a baseline here at 1 eventually. Okay, let's set out our parameters for our new period. I'm going to rewrite our function. I'm going to pull out the 1/2, leaving x minus 2 on the inside, and then a plus 1. I've taken care of the plus 1 here. Let's take care of this b value. So our new period would equal 2 pi over b, which is 1/2, which means our new period is going to be 4 pi. That's a nice number to work with since we want to split it up into fourths. So I'll go 4 pi. And I always cut it in half first, 2 pi. Cut that in half, which is pi. And then I go pi, 2 pi. This has got to be a 3 pi. It's helpful when you're dealing with fractions. Okay, so now what I'm going to do actually is, because I'm shifting to the right pi units, I'm going to add a 5 pi here. I'll take care of the end point of that first period. And I think we're about ready. So the amplitude of this is 1. So the max value will be up here at 2. And the min value will be down here at 0. But we have to be very careful, right? Because the original function is being shifted pi units to the right, as well as we've got a reflection going on. So I'm going to do our final function here in red. So I know that the sine function, whether it's reflected or not, will have zeros at the beginning, middle, and end, right? And it normally rises and then falls. But since we're doing a reflection, it's going to decrease, then increase, and then hit a max value here at what looks to be 4 pi. So I'd have 4 pi, comma 2. I'd have 5 pi, comma 1. I'd have 3 pi, comma 1. I have 2 pi, comma 0. And pi, comma 1. There you have it, guys. That is a graph of negative sine of x minus pi over 2 plus 1. All right, finally what we're going to do is we're going to identify and write a function for each of these graphs. Okay, so as I look at this first graph, it looks like our amplitude, this is going to be a sine function. So let's keep it simple. Here's a sine function, right, that cycles at this point for the first time. So it starts at 0 and it cycles here. This is 2 pi, so this is likely pi. So what I want is 2 pi over b to equal pi. So b has to equal 2. Okay, so I've identified something. Let's see if we've got a vertical stretch. Yeah, we do, of a factor of 3. Now, this hasn't been reflected because this is the standard position and orientation of the sine function, so that our amplitude is 3 and our a value is also 3. No reflection needed. Okay, it doesn't look like there's any horizontal shifts. We don't have to implement that. No vertical shifts. Therefore, this function would be y equals 3 sine of 2x. Okay, let's move to the next one. Okay, this looks like a cosine function, standard, right? Looks real nice from there to there. This value is pi. I have to kind of guess here, but I'm going to guess that this is 2 pi over 3. So if my cosine function cycles at 2 pi over 3, that's our period. Okay, that's going to be equal to 2 pi over b, therefore b has to equal 3, okay? Looks like we have a vertical stretch, no reflection involved. It looks like we have a max value of 2 and a min value of negative 2. Therefore, y would equal 2 cosine, whoops, almost wrote sine, of 3x. All right, let's move to the next one. Very similar. It looks like I have a vertical stretch. Cosine has not been reflected, so and it hasn't been shifted up or down, left or right. So I'm going to say that's 2.5, which I'll write as 5 halves. Cosine of, I'm going to go with x over 2. So it cycles after 4 pi. So 2 pi over b equals 4 pi. So b would have to equal 1/2. Okay, a lot of that's experience, but it is what it is. You got to get used to that. Okay, let's look at this one. Ooh, I've got a vertical reflection of a sine function. So I know a will be negative. Looks like it's stretched by a factor of 3. So y will equal negative 3 sine. Looks like I'm stretching this out to 6 pi. So 6 pi over b is equal to, oops, I'm sorry. 6 pi is equal to 2 pi over b. So b has to be 1/3. So that'll be x over 3. All right, cool. We got some vertical shifts going on here. All right, this is a good one. All right, this graph from here to here looks like a cosine function to me. And what it looks like to me is that this is a full cycle and it's 2 pi. So b is going to equal 1. All right, there's no horizontal shifts going on because its min value in this case takes place right here on the y-axis. Okay, so I can at least write cosine of x. Okay, I just have to work with some value for the vertical stretch. It looks like a reflection as well as a shift. So what I want to do, you guys, is I got to find the baseline. Everything before this question right here had a baseline at 0, but this one doesn't. So it looks like this goes up to 8, and it goes down to 0. Therefore, its baseline has to be at 4. So that is our vertical shift. Okay, and then we have to consider our amplitude, which is this length, which is 4. But we also have to consider the vertical reflection. So our end function is y equals negative 4 cosine of x plus 4. That was a good one. Let's look at this last one. Oh, this last one might be hard to work with. Well, we'll do it anyways. It doesn't matter. All right, looks like a cosine function from here to here. I'm going to call that 2 pi. I'm not sure if the textbook that I'm using would call that right. I don't know. But that would be a cosine function reflected, right? So I know that I'm going to have a reflection. And it looks to me like, okay, if this is 1, 2, 3, this is 4, this is 5, this is 6. Oh boy, this is a tough one. This point and this point represent the upper portion and the lower portion of the function. So its baseline is right here in blue. Here's the baseline. What did we say that is? 1, 2, 3. Okay, so we're shifted down 4 units. That's our vertical shift. Our amplitude looks to be a half. I'm going to say a half. And have we changed the period? No, the period is still 2 pi. So that's going to be, that's got to be our function. That's it. So y equals negative 1/2 cosine of x minus 4. There you go, guys. That's a crash course on graphing and looking at graphs and writing trig functions. So hope it went well for you. Let me know if you got any questions, and we'll move it on from here.